And we're down to the last section of the semester with the section 8.2, which has quite a few topics, but the one that we'll focus on is average value of a function, or how to use the integral that we learn to compute the average value. Well, we know how to compute the average value in everyday situations with discrete values. For example, anytime you want to compute an average, you would add up the values and divide them by however many values there are. For example, to compute the average score out of 4 exams, we can add the 4 scores and divide them by 4, the number of exams. We can try to apply it in case of a continuous function, which looks something like this. Let me pull down. Notice how if you have a function, now you have infinitely many values, but that's what the integral does. It's going to actually provide that sum. And then instead of dividing by number of exams, for example, or number of values, you can divide by the length of the whole interval. That's where the b minus a is coming from. Okay, so notice, see how I'm putting up a line which is kind of approximating the average. So the average is going to be a number, but it's going to be an average y value of a function on that interval. That's precisely what we're computing. So how you compute it, that's an integral from a to b of f of x dx dividing by b minus a, or since b minus a is a constant, you can pull that out in front of the integral and then compute the integral itself. So the notation we'll use is f average, or f with a bar on the top, f bar, to denote. So anytime you're asked for average value, that's what we have to do. So let's say I want to do 3 examples with different functions, or maybe a couple of examples, and then maybe an application. So let's say we have a function, x squared minus 4. Interval is from 0 to 5. So how we compute the average value of a function on an interval is 1 over b minus a, which is 5 minus 0, times the integral from 0 to 5 of x squared minus 4 dx. So we get 1/5 times the integral, which we keep it as a constant. So I keep the 1/5. I actually do not distribute it till the very end. Then I have the antiderivative, which is x cubed over 3 minus 4x, and we evaluate it from 0 to 5. We can plug in the 5. Remember, we can disregard the 0 if it's the bottom one, especially with just the x values. Be careful if you have exponentials, then you cannot just disregard them. But in this case, we can. So it's 1/5 times 5 cubed, that's 125 over 3, minus 4 times 5. So we'll get, I actually subtracted, so that's 125 over 3 minus 20. That's, I think, 125 over 3 minus 60 over 3, so I'm getting 65 over 3. So that's 1/5 times 65 over 3, and I'm getting, I think it's 13 over 3 if you reduce it with a 5, which is about 4.3. Again, you can use it as a fraction or a decimal in this case to get the idea. So that's what you get. Or you can, from here, you can actually get the decimal as your answer if you prefer not to deal with fractions. Okay. Now, same idea. We have a square root of x plus 1, and the interval is from 3 to 8. So how we set this up? So it's 1 over 8 minus 3. That's how come I got the 5. So you can put that at once. Times the integral from 3 to 8 of square root of x plus 1 dx. Now, I think we could have probably integrated it directly, but because of the x plus 1, you have to be careful. You want to actually use u substitution because, again, it's a more complex function. So, as usual, we substitute u for the inside function, x plus 1, and we take the derivative, which is just dx, or just 1 times dx. Then, as before, the x you can plug in into the u, so I'm getting 4, and then x equals 8 gives us u equals 9, and that's good because of the square root. That's going to help us later. So let's actually perform the substitution. So 1/5 stays, that does not go away, but then we get integral from 4 to 9 of u to the 1/2 power du. Then we integrate that, so I'm getting 1/5 times, the way I got 2/3 is because 1/2 plus 1 would give us 3/2, since we're dividing by a fraction, you actually flip it and you multiply by it. So I get 1/5 times 2/3 u to the 3/2 power, evaluated from 4 to 9. So then we get 1/5 times 2/3 will give us 2/15 u to the 3/2 power from 4 to 9. So what we do, again, I keep 2/15 on the outside as a fraction, then we can plug in 9 to the 3/2 power minus 4 to the 3/2 power. How I evaluate that? The half power is a square root. So square root of 9 is 3 cubed. That's how come we get 27. Then the square root of 4 is 2. 2 cubed gives us 8. So 27 minus 8, that's 19. And 2/15 times 19 will give us 38/15, which is about 2.533. Okay. Let's do the same thing with the third one. E to the x over 7. Interval is from 0 to 7. Let's take a look. So the f average value of a function will be 1/7, or 7 minus 0, which is just 7. Integral from 0 to 7, e to the x over 7 dx. We integrate it. So if you recall, 1/7 is the constant that stays. E to the x over 7, to integrate it, you keep it the same, but then you divide it by the derivative of x over 7, which is just 1/7. Then we can flip that bottom function, so we'll get 1/7 times 7. So a lot of 7's floating around here. E to the x over 7 from 0 to 7. But at least here 7's cancel, so you just end up with e to the x over 7. Now we can plug in. We'll get e to the 7/7 minus e to the 0. Which, remember, 0 you cannot disregard in this case because of the e. So we're getting e minus 1, which you can put in your calculator. E, I think, is above the division sign for graphing calculators. And that's about 2.718 minus 1, which is about 1.718. So that's how you would do it with simple problems like that, with simple meaning like you're given a function and an interval. Let's take a look at one application. And applications work the same way, kind of. A stock analyst plots the price per share of a certain common stock as a function over time and finds that it can be approximated by this function. S of t, which stands for stocks, I believe, but that's a price, equals to 37 plus 6e to the negative 0.03t. Where t is time in years since the stock was purchased. And then find the average price of the stock over the first 6 years. Again, this gives us an interval. So you can imagine interval is actually from 0 to 6 because it's the first 6 years since it was purchased, which means t equals 0. So the average price of the stock, or S average, is equal to 1/6 times integral from 0 to 6 of the function, which will get 1637t. If you recall with exponentials, we keep the 6e to the negative 0.03t on the top, divided by the derivative of the exponent, which is negative 0.03, evaluated from 6 to 0. So I clean this up a little bit. 6 divided by negative 0.03, we're getting negative 200. And then moving on down, let's plug in the 6 first. So we'll get 37 times 6. Minus 200 e to the negative 0.03 times 6, and then I subtracted minus 37 times 0 is 0, but I wrote it anyways, minus 200 e to the 0. So if we clean this up, I kept the first part the same, but then the last part gives us positive 200 because of e to the 0. We add them all up, so I got about 200 divided by 6. Do not forget to divide for average value. So we're getting 42.49, which was the average price within the first 6 years. And that's it for the last section of the semester. All right, hooray. Bye-bye.